Do I get a T-shirt?
You do get it.
Oh, fantastic. Okay, so I guess we should start. First things first, I wanted just to say that some of you came to me after the lecture yesterday with some amazing questions, like really provocative, interesting discussion. So please, that was fantastic. After today's lecture, of course, I will stay here for a bit and we can keep discussing. But also, I think some of the questions, especially the more provocative ones, like what would you say to someone who says the hierarchy problem doesn't exist? The questions like that are also very valuable for everyone to discuss. So if you have any thoughts along those lines that you want to bring up, don't be shy. If you're thinking it, chances are probably some other people are thinking it too. So please don't hesitate. The more discussion and debate, the better. And all of those questions were really very insightful and worth discussing. Okay, so where we finished off yesterday, I was about to discuss the question, could the Higgs be pion-like? And by pion-like, I'm not just meaning composite, like the pion. The pion is a composite state of quark-antiquark, and it has a condensate, a fermion, a quark-antiquark condensate, which is like the pion's expectation value. But what I mean by the phrase pion-like Higgs, I really mean structurally, the reason that it would be light being the same reason that the pion is light. What I'm going to discuss today doesn't always uniquely apply to the Higgs being composite. So it can apply to the Higgs being composite, but not necessarily. I will discuss a theory where the Higgs, the UV theory isn't even strongly coupled, it's weakly coupled, okay? So some basics about pions. So the pions emerge as pseudo-Nambu-Goldstone bosons, PNGBs, because at the QCD scale, the quarks condense, and that spontaneously breaks an approximate global symmetry down from SU2 left across SU2 right down to SU2 vector. And so, as we know from Goldstone's theorem, we'll come back to this in a bit, you expect to get, if it were an exact symmetry, you would expect to get massless particles. And it's like even more than massless. I think massless is a really imprecise way to talk about Goldstone's theorem. It really means particles that have no scalar potential whatsoever. As they change value, the potential energy doesn't change. That's a much more useful way to picture it in my mind. And in fact, we will come back to this as well. You can capture the physics of those pseudo-Goldstone bosons by working with the CCW, I'll say it pains me to say Z, CCWZ construction. Who has heard of this before? Not many people. Okay, very good. So this is a construction. We're not going to have time to really go into it in much detail. I'll discuss it in a little bit. But the basic way of thinking about the CCWZ construction is the following. You take the generators of the global symmetry, which have been broken, spontaneously broken. And for each one of those generators, you have a Goldstone boson. Okay, so those Goldstone bosons here, I'll call them pi I. This is very unhelpful notation, but I'm going to do it. Pi I, and here are the generators of SU2. And you can then work out what the low energy theory describing their interactions, their dynamics, and so on looks like by packaging them as in this way, as if they lived in. So this, you see, these are 2x2 matrices. So this exponential here is actually a 2x2 matrix. As if they were a linear representation of the symmetry that was broken before. So you can write down everything in an SU2 symmetric way, SU2 left cross SU2 right symmetric way. So this is a matrix that would transform under these two symmetries with a left 2x2 unitary matrix here and a right one here, and they don't have to be the same. You can write down the entire theory as if it was invariant as if this was a linear representation. It's invariant under these two symmetries. With this parameterization, then you can find out how the spontaneous symmetry breaking feeds in. This F pi is the pion condensate. So you can think of it as being like the QQ bar of VEV, just like the Higgs has a VEV. Here, QQ bar has a VEV because QCD is caused quark condensation. And doing that, it can be proven that you can essentially write down the correct low energy effective theory. And so, and this will be very valuable for us. And one way to see this already, one way that this is useful when we think about pions, is that we can see how the quark mass in the UV theory, this is just QCD, we know the UV theory in this case, how the quark mass feeds in to generate a scalar potential for the pions in the following way. M Q bar Q in the UV theory gives us, in the IR theory, something that looks like, so Q bar, you can think of Q bar Q as being this 2 by 2 matrix, which is this guy here, gives us something that in the IR theory that we would write as M pi squared F pi squared trace, actually, F pi, because I put a pi in here, trace of sigma. So you see here, this has the same SU2 left cross SU2 right transformation properties as this Q bar Q in the UV theory. And at the lowest order, we can expand out this trace. At lowest order, this gives us the pion mass. 1/2 m pi squared, pi 0 squared plus pi 1 squared plus pi 2 squared. Plus higher terms will be a quartic and quartic interaction and so on. Okay, and we know that m pi squared here is a quantity that is proportional to the quark masses. So if the quarks were even lighter than 4 or 5 MeV, then so too the pion mass would scale proportionate to that. Okay, so now we can do a spurion analysis to see, to try and understand structural features of this theory. So one thing that we can see straight off the bat is that the pions don't have a shift. Yes?
I have a question.
Yep.
If the purpose of this is to make it so that the mass related to the Higgs is not super small, wouldn't this make the problem twice as worse? Because now we need a Higgs quark mass that's basically twice as small as the Higgs mass?
I'm not sure I understand the question. So is the question that, so here the pions are light. Okay, I think I understand your question. So and I'm going to answer it without repeating the question, but let me plow ahead and see if this works. Here you see the quark masses set the pion mass. So if the quark masses were super light, the pion mass would be super light, and we'll see that we'll have a similar thing could happen for a pion like Higgs. But the interesting thing here is that the quark masses can be small without any fine-tuning. Because they break, there's a chiral symmetry in here. I have a chiral symmetry that would be that Q goes to e to the, let's say, I theta Q. And Q bar goes to e to the I theta Q bar. And this parameter breaks that symmetry. So in the UV theory beyond the standard model, there's no problem with the quark masses being small. They're essentially a spurion for explicit breaking of a chiral symmetry. And so we don't, unlike the Higgs, which we'll come to, unlike the Higgs mass, which is quadratically sensitive to whatever's going on at the UV scale, the quark masses can be naturally very small, which would explain then why the pion masses can be naturally very small. Does this answer your question?
Not really.
Okay. Can you yes, come back to me with the same question if I haven't answered it when I get to the Higgs part of it. Okay, excellent. So we know that if the quarks had been massless, the pions would have been exact Goldstone bosons. And so there would be no scalar potential. And in that limit, they would have had what's known as a shift symmetry, where, for instance, pi 0 could go to pi 0 plus some constant. This is local. It's actually non-abelian, so it's not so simple. But if you do a small constant shift, the theory would have been invariant. And in fact, this shift symmetry is something you associate with Goldstone bosons in general. And you see that the kinetic terms, for instance, for the pions, we'll come back to this, but without the gauge interactions, the kinetic terms respect this shift symmetry, because if I act on this with d by dx, where x is any of the four space-time components, the constant just gives you nothing, because differentiating a constant gives you nothing. Okay, so we can see that here, m pi squared we can think of as being a spurion that explicitly breaks a shift symmetry. Okay, so far so good. So we can understand then, we can understand in the IR theory why they can be naturally light, because this is the only spurion, the only parameter that's breaking the shift symmetry, which would have made them exactly massless. We can also understand why they would be naturally light from the UV theory, because the quark mass breaks a chiral symmetry explicitly, so that's a spurion too, and so it can be small. Also, we see that this looks SO3 symmetric, right? It's treating all of them so far in the same way, which came just from this trace.
Sorry.
Yep.
So the difference with the pseudo-Boltzmann boson is that we are breaking explicitly.
Yes.
Chiral symmetry.
Yes. So when the quarks condense, so the question was the difference with the pseudo-Goldstone boson is that we're breaking the symmetry explicitly, and that's exactly correct. So there's two breakings here. There's the spontaneous breaking that occurs when the quarks condense, and there's explicit breaking that's there the whole time because of the non-zero quark masses. Yep.
The SU2 vector is broken if the mass are there, or if the mass of the quarks are different.
So you could write this. I could write this as SU2 vector cross SU2 axial. That's maybe a more useful way. And you see that the vector is never broken.
Not even with the mass.
No. Yeah. Question. So it was the SU2 axial, which was spontaneously broken and gave you the Goldstone bosons.
SU2 axial isn't really a group.
Yeah, it's not really a group. I know. This is why.
It's to itself. It
Yes.
goes using the vector.
Yes. But this is why I wrote it in this way. Yeah. But you can think of it as being the SU2 axial part of this was spontaneously broken, which gave you the Goldstone bosons, but it was also explicitly broken by this, which gave you which means that they aren't exact Goldstone bosons. Okay, so yes, you can see that this is also approximately SO3, not approximately, this is actually SO3 symmetric. So there's two symmetries here to think about. There's the SO3 symmetry, which is SU2, if you want to think about it in that way. And there's also the shift symmetry of the pions, which has been explicitly broken by the pion mass, by this term here, which came from the quark masses. However, there's a problem, which is that the kinetic term for the pions doesn't respect either of those symmetries. The kinetic term for the pions, you've got just the usual kinetic term for pi 0. And there's the, we can package pi 1 and pi 2 into pi plus or pi minus. Pi plus, for instance, being 1 over square root pi 1 plus I pi 2. And then the kinetic term looks like this. And you see that not only, so this respects the shift symmetry, but this doesn't because of the gauge field. And this breaks the SO3 symmetry because you're not treating the pi 0 in the same way as the pi plus minus because of the gauge interactions there. So following the same effective field theory logic, we should appeal to the totalitarian principle. If there's some UV scale, which there is in this case, it's the QCD scale, then this implies that we should expect terms in this scalar potential, which would also look like, let's call it delta L, which would also look like E squared, let's say over 4 pi squared, whatever's going on at the cutoffs, let's say lambda QCD, for instance, squared, times pi plus squared. There's nothing to forbid a term like this. And so you see that just using the same arguments that I described yesterday, you expect quadratic sensitivity of the charged pions to whatever the UV scale is, which means you don't expect the charged pions to have the same mass as the pi 0. It turns out that this is, of course, correct. The charged pion isn't the same mass as the pi zero. You can look at their mass difference, and you see that if the just from m pi zero squared minus m pi plus squared, you can see that this term here would be too big. It would be too big for the observed mass difference if lambda were bigger than about 750 MeV. So there are two possibilities. Imagine you didn't know about QCD. So you're just working with the symmetries in the effective field theory, and you're trying to guess about what's going on in the UV. There are two possibilities. It could be, or let's say three possibilities. The first possibility is you don't understand what you're doing. You're making some error in your logic. The second possibility is that this is correct, and that the UV scale really isn't too far away. It's at around 750 MeV. Or the third possibility would be that this is correct, but actually there's been some fine-tuning between different contributions that are coming from the UV at the QCD scale or whatever, which cancel one another to give you a much smaller contribution, such that this stays small enough to match the observed value, even though the UV scale is far away. Yep. Pardon? Yes. Well, there's no reason it should be there, right? Because pi zero. So yeah. So okay. Sorry. Yes. The question is, the observation is that there's no symmetries that forbid you from having these contributions, but couldn't you also have them for the pi zero? But the pi zero doesn't couple to the photon. So if we look at the spurions, the parameters that the pi zero knows about, it's got a shift symmetry here, and the only thing it knows about is m pi squared. So in principle, we could have a contribution that looks like m pi squared pi zero. Right? There's no other thing you could write down, because that's the only spurion for breaking shift symmetry of the pi zero. And so that's already there. We've included it. So the answer is no. That because the neutral pion doesn't couple to the photon, there's no additional parameter that breaks its shift symmetry, whereas the charged pions do have that. Very good question. Yep.
So the naturalness argument is telling you that the new physics is going to appear at this scale.
Right. Exactly.
But why do you understand like it's going to be bigger?
So the question here is the naturalness. The argument is telling you that the UV physics should show up at this scale. So why did I say it could be bigger? Because imagine you're working in the IR, in the effective field theory, and you don't know what the UV scale is. You would make this argument and say new physics should show up. But if the UV theory is fine-tuned, it's possible that the UV scale could be very far away, and there are different contributions.
But then you are fine-tuning that.
Right, exactly. So then there would be fine-tuning. So naturalness doesn't tell you, the naturalness approach to trying to guess at what's going on in the UV doesn't tell you that you can't have fine-tuning. You could have fine-tuning. You would have a question if you did, but you could have fine-tuning. So what route did nature pick? Nature here picked a route where indeed some new states show up here. This is essentially the rho meson. And in fact, you can calculate this mass difference, and it's essentially proportional to the rho meson mass. So everything works very beautifully. The sort of naturalist type reasoning about what and counting and studying spurions works very well at guiding you as to what scale you should expect new physics, in this case the UV physics, to show up. How would this look for the Higgs? We're going to get into this in more detail, but we can follow the exact same logic. We can look at the standard model Lagrangian, and there's one term that's worth studying a lot, which is the top quark Yukawa. And you see here, if the Higgs were a PNGB, that this interaction explicitly breaks any shift symmetry that the Higgs could have had. So the usual argument that you will see, or hopefully the usual argument you would see, would be to conclude, following similar logic, that then if the Higgs were a PNGB, there's nothing to forbid terms contributing to the potential that looks something like, let's say, 6 lambda top squared. We say 6 because the counting of this breaking includes the multiplicity of these particles. 4 pi squared. Then some UV scale, we don't know what it is, Higgs squared. And you see that these contributions would be too big, similar to line of argument to this, if lambda is bigger than, say, 500 GeV or so. By too big, I mean you need to start fine-tuning. You would need to start having fine-tuning in the UV theory if this were to happen. So even before we've written down any explicit model for a PNGB like Higgs, we can immediately see where the big stumbling blocks are going to be. Because already the Spurion analysis, following the Spurion analysis, we look at interactions, even in the IR theory, which explicitly break a shift symmetry, and we're already concluding that the UV scale, if the Higgs is a PNGB, can't be too far away. There's a similar thing as well for the Higgs gauge interactions, the electroweak interactions, which is really analogous to this, but it's a little less constraining. Okay. So we can see what's going to happen. Are there any questions up until this point? No. Okay. So now I want to sort of sketch the nitty-gritty of what pion-like Higgs theory would look like. We don't need to go into too much detail, and we're going to put a bit more flesh on these general arguments. So for a PNGB like Higgs, essentially what you have, you rely on Goldstone's theorem. Who's actually read the paper? Nobody? I suggest you do. It's a very nice paper. Goldstone's theorem, which tells you that if you have a global symmetry G, which is spontaneously broken to a smaller global symmetry, this would be a subgroup of G that we will call H, then you would get a Nambu-Goldstone bosons. Bosons, which essentially describe the vacuum manifold that we will call G over H. So this is sort of getting a little bit mathematical. The way I would say you should think about this is the following, that you start off with G, which is a linearly realized symmetry, and then the Goldstone bosons, actually, I always feel like spontaneous breaking is a bit of a misnomer, because the symmetry is always there. It's just that it gets rearranged and repackaged in a different way. So really, the Goldstone bosons non-linearly realize this part of the symmetry, and they transform in a very in a completely unique way, determined by that spontaneous symmetry breaking. And so we say this is non-linearly realized, this part of the symmetry. Plus, there's this leftover bit, which is just a standard symmetry, and we say that that is linearly realized. I think the sort of Mexican hat potential is a really useful thing to think about in this context. So who has a picture in their mind when I say Mexican hat potential? Great, because I was really worried about having to draw it. So if you think about the Mexican hat potential, you start at the center, and then you say you're at high temperatures, and the effective mass is positive. Say this is just like a abelian Higgs type model, except you don't even have it's a global symmetry, not a gauge symmetry. So you start at high temperatures, and it's not a Mexican hat, because the minimum is at the origin. Then the temperature goes down, and the effective mass squared becomes negative, and the field rolls down to the bottom of the Mexican hat, or wine bottle, whatever way you want to describe it. And The Goldstone boson corresponds to just moving around the bottom of that potential. That's a really good picture to keep in mind, even when things get very mathematical. That's a really good picture to keep in mind. That's why it's massless. If you want to move it from one point on that circle to another point on that circle, it'll cost you 0 energy because you're not going up the potential at all. Whereas the radial mode, we call it, the Higgs, if you want to move it around going outward from the outward or inward in the potential, you actually have to move up or down. You have to move up the potential from that point, and that costs you energy. That's why that mode, the radial mode, has mass. It's a super physical picture. And so that's what's really going on here. These Goldstone bosons, there's a more complicated group, but actually the Mexican hat is still a really good picture to keep in your mind. Really can have much more complicated groups, but you're really talking, the things you're talking about are really just talking about moving around some manifold that's all at 0 energy or at the same energy. So it doesn't cost you any energy to move around it. It also reveals why the Mexican hat potential is a really dumb thing to think about when you've got a spontaneously broken gauge symmetry. You probably hear people saying that a gauge symmetry isn't a symmetry, right? A global symmetry is a symmetry. A gauge symmetry is a redundancy. This really reveals that fact. Because if the actual physical potential were a Mexican hat, there'd be some mode which, if you change its value to go around, it costs you 0 energy. There'd be a massless particle. And there isn't a massless particle. There's no Mexican hat potential for a spontaneously broken gauge symmetry. We draw it that way because we like to think in the UV, and we sort of separate out the longitudinal modes and think about them separately from the gauge fields. And so we draw a Mexican hat potential, you go down, but they got eaten. But if they're eaten, then why are you drawing a potential where there's 0 vacuum energy? So it's a bit misleading, that picture, for spontaneously broken gauge symmetries. Okay, so now we can start to build a recipe. As I said, we do model building because it's a modest endeavor. We're trying to guess at what's going on in the UV. We're not trying to decide, what it should be. If the Higgs is a PNGB, then we have a recipe. We would start with some global symmetry. We'll call it G. Some subgroup of that might be gauged. We'll call that G tilde. Can anyone tell me why we will have to gauge a subgroup of G? Any guess is welcome. Yep. It's the standard model. The Higgs couples to SU2 left cross U1 hypercharge. So we're going to have to. This is non-negotiable. This will be spontaneously broken to some other global symmetry H, of which some subgroup will be gauged, because also gauged, because we need to keep SU2 left cross U1 hypercharge there for the Higgs to interact with it. So there has to be some, when this breaking happens, it can't be breaking the standard model gauge group. Otherwise, the W and Z bosons would be very heavy. They would be at the scale of spontaneous symmetry breaking of G, which could be like a TeV or more, as we will see. Furthermore, there's going to be explicit symmetry breaking. Because the Higgs gets a potential. So there's going to have to be some explicit symmetry breaking around. And we'll see that that's actually a problem. It's not a feature. So how many PNGBs will we get at the end? We will get NG PNGBs, which would be the dimension of G minus the dimension of H. Plus, we've gauged some part. So of all the parts that were spontaneously broken and were gauged, those PNGBs will become eaten. And so we won't see them in the low energy theory. They don't correspond to 0 vacuum energy moving around the bottom of the Mexican hat potential. And so for every gauge symmetry that was spontaneously broken, we will lose, every generator, we will lose a Goldstone boson. And we will require that NG is greater than or equal to 4. So why is that?
SU2 cross U1.
Yeah, the Higgs has 4 degrees. The Higgs doublet has 4 degrees of freedom. It's 2 complex scalar fields. And that H tilde at least includes SU2 left cross U1 hypercharge. All right, so the simplest example of a model with this structure, it's actually ruled out, but I'm going to experimentally, but I'm going to show it to you, unless the symmetry breaking scale is very high. I'm going to show it to you because it's very straightforward and gives you the main features before we can move on to more complicated examples. Has G being SU3, a global SU3 symmetry, where we gauge an SU2 subgroup for SU2L, and there's a U1 hypercharge essentially sitting around the whole time. And so the nonlinear representation for this field looks like a fundamental of SU3. So we call it sigma 0, and then we do the same CCWZ construction, where we have all of the goldstones, all of the generators now that are spontaneously broken in SU3, some spontaneous symmetry breaking scale, and ultimately this becomes, we can write this as F over H times an SU3, what looks like an SU3 fundamental. So we'll have I H1 sine of H over F, I H2 cosine, oh no, sorry, sine of H over F. And H1 and H2 are just the 2 Higgs complex scalars. And in here we have something like, we have H cosine H over F. This is just what pops out if you do this construction. And H here is the square root of, let's call it H dagger H. Okay, so straight off the bat, we can extract the gauge interactions of a PNGB-like Higgs, because just as we did for the pions, let's call it kinetic, we have covariant derivatives. Sorry. Here, where the covariant derivative just includes the gauged subgroup. So this is the covariant derivative you can think of as being a 3x3 matrix that acts on on sigma here. But the gauge fields are only living in the top 2x2 corner of that, because we're only gauging an SU2 subgroup. And so, for instance, if you expand all of this out, you act with that 2x2, the full 3x3 matrix, of which the 2x2 top component contains the SU2 gauge fields. You will find the following expression. So you get lots of terms, but one of the terms you will get it looks like this: F squared sine squared H over F W mu plus W mu minus, and other terms, like involving the Z and so on. So we see here that our prediction for the W mass, mW squared, in a theory of this form, is G squared F squared sine squared of V over F, where V is the vacuum expectation value of the Higgs. That's where the W mass is going to come from. What's different between this and the standard model prediction? Anybody? Pardon? We don't have F, you mean? Or?
In the standard model.
In the standard model, exactly. So in the standard model, you just have G squared V squared. So we see that we're actually predicting that the electroweak gauge bosons have masses that depend slightly differently on the vacuum expectation value of the Higgs field in these models.
Standard model is the small v limit.
Yes, exactly, or the infinite F limit. Yeah. And so, if the masses depend slightly differently on the VEV of the Higgs, then the Higgs couplings will also be different. So you can extract the Higgs couplings. in the usual way, just from the dependence of the mass on the VEV. So to get the Higgs coupling, you have V plus H in here, and you do a Taylor expansion in the Higgs, and you pick out the first term. That's the Higgs coupling. If you're doing a Taylor expansion, you're just taking a derivative. So you see that dmw squared by dv is 2g mw cosine of v over f. If you want, you can do this exercise yourself. I'll give you a more interesting one in a second. Whereas in the standard model, it's just 2g mw. The infinite f limit is cosine of 0, which is 1.
G squared.
Yes. Yes. No, sorry, there's a G in MW here. Yep. Okay, so we see that compared to the standard model, if the Higgs were a PNGB, then, so I'm taking the ratio of this Higgs coupling to 2 W's versus the standard model prediction. I'll call that the coupling modifier, i.e. what's packaging it compared to the standard model prediction. The coupling modifier is that C Higgs, and actually it's the same for the Z, so we'll just call it vector vector. Higgs vector vector is cosine of V over F. And if F is large, then we know that this is something like 1 minus a half V squared over F squared. All right. And it turns out this is for an SU3 theory, which is actually experimentally ruled out because it violates a thing called custodial symmetry. Very happy to talk about it after the lectures if you like. But this fact is actually a very, very general one. Okay, so if the Higgs is a PNGB, the Higgs couplings to the vector bosons will not be standard model-like. Exactly. Yep.
So in the QCD case, our PNGBs are pseudoscalars.
Yes.
So we know the Higgs is 0 plus plus. So how do we ensure that we get the right quantum numbers?
That's a very good question. So the question is, in this case, the pions were CP odd, but the Higgs is not. So how do we ensure we get the right quantum numbers? Here, how do we ensure? It's a very, very good question.
I don't think we're breaking any axial symmetry. The breaking symmetry factor doesn't involve an axial symmetry. So.
Yeah, can I come back to that and try and answer it? If not today, then tomorrow in the lecture, because I think indeed it relates. I'm not going to give you a crappy answer.
Okay.
I'm not happy with the answer I have in my head. Yeah, Nathaniel.
Who's C? So it's CGR, who's C?
Yeah.
So but you have to define C with respect to standard model. So that's a standard model C.
Yeah. This is the correct answer, but I want to.
Could you repeat the correct answer just for?
Well, the thing is that C is an ambiguous thing, right? And so it's C relative to what, and how that ties into to space-time symmetries. But I think I can try and do even a bit better for tomorrow. It's a very, very good question. Okay. Furthermore, however, we see that this is all very analogous to the pion situation, so we should expect at the same time to have Higgs mass corrections from the UV that scale as g squared lambda squared, because when we gauged this global symmetry subgroup, we actually explicitly broke the global symmetry in exactly the same way as the pions here. The gauging of electromagnetism explicitly broke the SU2 cross SU2 symmetry. And so that's why it generates a mass for the charged pions, a mass correction for the charged pions. Okay, what about the fermion interactions? the Yukawa interactions. So let's call it, I'm using lambda, is we would write for this theory as lambda t q dot sigma t right. But you see here, sigma was a vector with 3 entries here. So this q object here can't be the usual q that we have in the standard model, which is 2. Okay. So what are the options? One option is to do the ostrich and bury your head in the sand and just say, well, okay, I'm not going to worry about that. I'm just going to say that Q doesn't have a third entry here, that there's no field there. So I'm going to pretend that it's a 3-plet, but it doesn't have that entry. But you see that then this explicitly breaks the symmetry, because for this thing to be SU3 invariant, I have to be able to do an SU3 rotation on this field and end up with the same term. So that explicitly breaks the symmetry. So you then would expect the outcome of that ansatz to be that you've explicitly broken the symmetry. So you should get a quadratic sensitivity to the cutoff in the usual way. Let's call it 6, sorry. 16 pi squared. No, I want to call it 3. Pi squared lambda squared. And you will see that this is indeed borne out. One way to see this is that we can be a little bit smarter, we can work a little bit harder, and actually start off with this field in there, really make this SU3 symmetric. If we really make it SU3 symmetric, then we're going to get no mass corrections to the Higgs. We're going to have no problem. Apart from the fact that we have not observed this T particle. This T particle wouldn't get mass from electroweak symmetry breaking, so it should be a massless, literally a massless fermion, right? I can only get one mass from this interaction because there's only one opposite chirality fermion to pair up with here. So we would have a massless top partner field, which is experimentally ruled out. We can modify the theory. We can say, well, okay, I will explicitly break that symmetry in a different way by actually pairing this field up, this fermion, with its own partner, and then I've got a Dirac mass for it, so I can make it heavy. But this is explicitly broken the symmetry because I've just pulled something out of an SU3 representation and put it in my action. So I've done violence to the symmetry. Yep.
Is this a Majorana mass term?
A Majorana? No, this is not. This one is not Majorana because I can't write a Majorana mass term because this thing is charged under QCD. So if there were no QCD, I could have gone down that route and I would have gotten a similar result. But because of QCD and hypercharge in this case, we can't do that. Great question.
So is that TTC the same as T-bar T?
I don't like Dirac spinners. So, so yes, you could think of it as being like T-bar T. But I think it's useful to work with Weil spinners because then you can remember what's charged under which gauge groups in this structure more easily. Okay, so then I've got this theory, and actually I can actually do a loop calculation. I can integrate out this T field and see what happens. And indeed, you get a correction to the Higgs mass squared, which scales as 3, the usual thing. I keep writing it. I should just put it in the corner and refer to it. 16 pi squared mt squared. And of course, this is what should happen, because mt is the only parameter in this part of the story that's explicitly breaking the SU3 symmetry. So it seems that whatever we do, we can't get around this. And what this tells you here is something quite general about PNGB-like Higgs models, which is that you tend to have an extra fermion flying around, which we would normally call the top partner. We call it the top partner because it is the thing that completes the symmetry and lets the Higgs be light. But there's no free lunch. That top partner, we haven't seen it, so it must be heavy. And the only way to make it heavy is to break the symmetry that we were using to make the Higgs light. And when we do that, we get corrections to the Higgs mass. So if any of you are familiar with supersymmetry, you will know of a similar story for the stop quarks, and it's really for the same reasons.
So if MT is very heavy, doesn't this make the Higgs mass now have to be super heavy?
Exactly, that's the problem. So the question was, if MT is big, doesn't that mean that you're predicting the Higgs to be heavy, and that is exactly the problem. So, to match, if you include this loop factor to match the observed Higgs mass, this would need to be less than about 500 GeV. We have not seen new SU3 charged fermions at 500 GeV at the LHC. They would have stuck out like a sore thumb, and they didn't. So that's a puzzle. Okay. Now, I want to try and quantify the fine-tuning in this class of theories. And I can do that quite straightforwardly. So what you will get when you integrate out fields like these top partners is quadratic corrections, but those quadratic corrections, they're not really functions of Higgs itself. Whenever you have PNGBs, you always get these trigonometric factors. So if you do this, you can do the exercise yourself. You see that the potential for the Higgs, at least coming from the top sector, looks something like, I'm going to call it beta now, just because I'm bored of writing. Or let me call it something. I'll just write it in. The top squared over 16 pi squared, f squared, the UV cutoff squared. This could, for instance, be the top partner mass. It could be mt squared. And that you will typically get corrections that I'm going to parameterize in the following way. We say 1 minus r sine squared of Higgs over f plus, I'm going to parameterize it this way, sine to the 4 of Higgs over f, and so on. Now, the coefficients of these terms are not exactly these numbers. They're UV dependent, so they will be order 1 quantities, but this is what the form of the potential will look like. And so, but this potential has to have a minimum that gives you the correct Higgs vacuum expectation value. This is like a wine, or a Mexican hat potential, except as a function of sine of Higgs over f. Okay, so these are order 1 numbers. But the typical vacuum expectation value when you minimize this potential, I'm going to come back to r in a second, so forget about r. If these are order 1 numbers, is either going to be essentially 0 or something like f or pi f or something like this. And so to get a small Higgs VEV, you will need to do some fine-tuning. Why do we want a small Higgs VEV compared to f? Yep. Precisely, exactly. Because already we know that the Higgs couplings to vectors are pretty standard model-like. It's sort of the, let's say, the 10% level. So we know that this term here has to be like 10% compared to this. So empirically, just from the LHC, we know that V over F is sort of small. If we want V over F to be sort of small, then you're going to have to fine-tune a parameter. I've parameterized this by R, but you could parameterize it in many ways. So whatever the UV physics does, it's going to give you something that gives you, it has to give you something that gives you a small Higgs VEV. We can actually calculate the Higgs VEV. We differentiate this potential and find the minimum. So we differentiate and set it equal to 0. And we find that R has to be 1 plus sine squared V over F. You can do this exercise yourself. And so we see that R, has, the 1 bit is exactly canceling this. So you need the coefficient of this to be small, plus some small correction. So you expect these numbers to be order 1, but actually this number has to be small. This number here has to be sine squared V over F if we're going to have a minimum for the Higgs, which is at Higgs equals V. But we can actually quantify or attempt to quantify the amount of fine-tuning. This is known as the first sort of attempt at this, I believe, was by Barbieri and Giudice. And how can you quantify it? It's a fun exercise. Because of time, I'm not going to go through the whole exercise, but I do recommend you do it. If you do it, consider it a homework problem. And if you have any problems doing it, if you want to try and do it, it's no obligation, and you try and do it and you can't, then I would be very, very happy to discuss it tomorrow or something over coffee or whatever. So consider it a very, very optional homework problem, which is the following thing. I'll just put it up here. If we want to quantify the fine-tuning, or attempt to quantify it, one way to do that is to look at how much the IR predictions change if we change the UV parameters. So if a small change in a UV parameter makes a big change in the IR prediction, i.e. the prediction in this case would be the VEV of the Higgs, V, then you would say that the theory is fine-tuned. So how can we quantify that? The way to quantify it in this case would be to take the logarithmic change of sine squared v over f, which is essentially the logarithmic related to the logarithmic change in v, the IR prediction. You have to predict the right Higgs vev in your theory. And in this case, the parameter we would tune would be r. So we take this with respect to logarithm of r. If there are other parameters that you might want to consider, these should really be partial derivatives. By logarithmic derivative, you're probably very familiar with this, but you can think of it as being the fractional change. It's right. What's the logarithmic derivative? It's d of the thing divided by the value of the thing. So you consider it as a fractional change. So what fractional change do I get in sine squared v over f for a fractional change in r? So this is a very nice quantifier. You can do this calculation and you find out that you get 1 plus 1 over sine squared v over f. And so we normally call this delta. I don't know why we chose that, but that sort of quantifies the fine-tuning. And so if delta is big, there's a lot of fine-tuning. A small change of a UV parameter leads to a big change of an IR prediction. And this is what you get. And you see that this is 4. We know that V over F is small from observations. So ultimately, this looks like it's scaling like F squared over V squared, if you expand out the sign, which is, we know that V squared over F squared is small. So F squared over V squared is big. So this is typically fine-tuned. And what you then find, we're calling the deviation in the Higgs couplings here, we'll call the deviation delta. Higgs VV is 1/2 of V squared over F squared. We then see that the fine-tuning in these theories is very tightly linked to the observed values of the Higgs couplings, the deviations in the Higgs couplings. So the fine-tuning here, you can just plug in the two numbers, and you get something like 1/2 delta Higgs VV, where delta, as I said, is the deviation from the standard model, so this thing here. So for a more and more standard model like Higgs coupling, delta becomes smaller and smaller, and your theory becomes more and more fine-tuned. Okay? So this is a very broad, we will play with this concept in the next 2 parts of this lecture. But this is a pretty general statement for PNGB-like Higgs models. You see a similar behavior actually in supersymmetry as well. So it's something that sort of tends to show up in symmetry-based approaches to understanding the hierarchy. But it's very clear and quantifiable in the case of a PNGB-like Higgs. Are there any questions about this? Yep.
So in the original hierarchy problem is we have these quadratic, but even with this, it still looks like the Higgs corrections are quadratic in masses.
Yes.
It's like, did we fix anything?
Did we? Yeah, that's a really great question. Did we fix anything? That was the question is, did we fix anything? But the curtains that were draped around this were that we were originally worried about quadratic divergences, and then we've still got quadratic divergences. And indeed, so what this is doing is in some sense revealing something quite important about how one might think about the hierarchy problem, because the hierarchy problem only exists if the UV theory is predictive, right? If the IR observations can be predicted, calculable within the UV theory. And so that's an expectation. What I said before was very broad brush. The typical expectation is that you would have quadratic sensitivity and so on. And of course, as we know, we can calculate in principle atomic physics from the standard model. It'd be very, very hard. You need to be able to derive nuclear physics from QCD and so on. But in principle, you can take the standard model and predict everything that happens at longer length scales that involves standard model observables. And what we've done here is we've actually written down a calculable UV theory and shown that what we expected to happen happens. And in some sense, it's become more robust because we can quantify, for instance, the fine-tuning. This is only one part of the fine-tuning story, which is V over the Higgs vev, the fine-tuning you have to do to get the Higgs vev right. There's another part, because there are 2 IR observables in this case. There's the vev and the Higgs mass. And there's fine-tuning related to the Higgs mass, which you can quantify in this way. So it's made things very quantifiable. And it's revealed that so far we've not really achieved anything because it's just telling us what we knew. But these two facts will then help us focus on trying to find theories which don't have these problems. And so it will help us get there. Yep. No, because I think the question was, can you see this depending on whether you're talking about the Higgs mass in the MS bar scheme versus like the pole mass or something like this? So that's a really, really good question. So this shows up when you have a UV theory in which you can calculate the Higgs mass. If I take the standard model and compare the Higgs mass parameter in the standard model in MS bar scheme to the observed pole mass, I can never see this. You will never ever see it because that's just a standard model. The standard model alone does not predict its own parameters. So you will only see this showing up if you have a UV theory where you can then calculate what the prediction for that mass parameter is. It's a really, really good question that you ask there. Yep. In the effective theory, by definition, essentially, the parameters in the effective field theory cannot be calculated. They're not predicted within the effective field theory itself. It's only when you have a calculable UV completion that you see these things. And we know the standard model has to be UV completed. Yep. Excellent question. OK. By the way, if you perform this exercise as homework, optional homework, I would suggest you do two more things. One would be see how this fine-tuning changes if I rescale. If I work in terms of, let's call it R tilde, which is just some constant, let's call it kappa, times R, does the fine-tuning prediction or quantification change? And the second part would be to take this a step further and calculate the fine-tuning with respect to R tilde. So d log sine v sine squared by d log R tilde. If R tilde is some general function of R, does the fine-tuning change? It's an interesting exercise. I'm not going to tell you the answer. If anyone has a go at it, we can discuss it tomorrow, but it's quite revealing. OK. So now we want to see how bulletproof these general arguments are. Actually, no, sorry, I can use this board over here. We want to see how bulletproof these general arguments are. Are there other possible UV completions of a PNGB-like Higgs nature which don't have these issues? I want to talk about two. The first is known as the twin Higgs. Who's heard of the twin Higgs? A few people, OK. So the twin Higgs was written down about, I guess, is it really 20 years old? It's almost 20 years old. Well, by Harnick, Chaco, Go, and then it's been, there was related work on folded SUSY and things like this with other collaborators. But the idea is to really focus on that bit there with the colored top partner masses and say, how non-negotiable is that? And it turns out that it's negotiable. However, it would require a very interesting UV structure. So why is it negotiable? So the twin Higgs model starts out not with like an SU3 symmetry or another symmetry you see for composite Higgs models or PNGB-like Higgs models is SO5. It starts out with an SO8 symmetry, which is spontaneously broken to SO7. How many Goldstone bosons would we have then? 7. We would have 7 Goldstone bosons. So that's too many. But the idea is that you have, so this is the spontaneous breaking. You would have explicit breaking in addition that explicitly breaks SO8 to SO4 cross SO4. Furthermore, we would gauge the SU2 weak subgroup. This bit here will be the standard model Higgs part. And we'll gauge this SU2 weak subgroup. So by the Goldstone counting rules we give over here, you see that 3 of those 7 Goldstone bosons get eaten by this SU2, let's call it weak twin, SU2 weak twin. They get eaten. So we actually only get a leftover with 4 Goldstone bosons, which would be our Higgs doublet. Okay. What nature does this explicit breaking show up in? Well, it turns out that one way to see this isn't the only way to think about it, by the way, but one way to think about it is if you were to have the standard model and an exact copy called the twin standard model, and the 2 of them have an exchange symmetry. So actually, I should have said this. We have explicit breaking of SO8 to SO4 cross SO4 cross Z2. Z2 is the exchange symmetry. And what's interesting is that this is sufficient to enforce, if you recall the accidental symmetry story yesterday, accidental symmetries are symmetries that emerge, extra symmetries that emerge at low energies. And if you think about it in these terms, if I have, if I write the Higgs doublet of this sector, if I write Higgs squared, then we could write it as the 4 components, Higgs 1 squared plus Higgs 2 squared, blah, 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 Higgs 4 squared. And the same for the twin. I'll put the twin in the top index just to make things, no, I'll put it down here. Higgs 1 twin squared plus blah, blah, Higgs 4 twin squared. Then the quadratic action on its own, let's say I have m squared, has Higgs squared plus Higgs twin squared. Just because we have an SO4 symmetry here, that's these 2 SO4s, and an exchange symmetry which says that if I swap these 2 things, then the theory has to be invariant. But you see, this, I write it like this plus this, and I've got full SO8 symmetry. Yep?
Shouldn't it be semi-direct, right?
The question is, shouldn't it be semi-direct product? Sure, if you like.
Just to be sure that I'm...
Yes, yes. But you see here, so that you now have an accidental symmetry, which means that the most relevant operators, the things that are most important at low energies, have more symmetry. They have a full SO8 symmetry, which is really the magic of the twin Higgs. Which means that then if we play the same game, we look at the spurions, we write down all of the terms that are allowed by the symmetries, then we would have something like delta V. We expect to have the same thing, 3 lambda top squared over 16 pi squared, because the top Yukawa breaks the shift symmetry of the would-be Goldstone bosons. We've got the gauge contributions, electroweak, 16 pi squared. Sorry, I'm starting to get sloppy because I'm rushing. Times some UV cutoff. The UV cutoff doesn't have to be the same for both sectors, but I'm just trying to get quickly to the answer. And you see then that you get Higgs squared plus Higgs twin squared, which respects the full SO8 symmetry, so it can't generate a mass for the Goldstone bosons. You only get a mass for the Goldstone bosons if you break the global symmetry that was spontaneously broken. So this makes the standard model Higgs, when it emerges as a Goldstone boson of this spontaneous symmetry breaking, will be insensitive to these corrections, which is very neat and very, very clever in my opinion. At the quartic level, you will also get corrections which look similar. Let's just focus on the top sector, 3 lambda top squared over 16 pi squared. There'll be some logs. But then you'll get terms that look like Higgs to the 4 plus Higgs twin to the 4. This is fully consistent with these symmetries in the Z2. but it is not consistent with the full SO8 symmetry. For it to be SO8 symmetric, it would be Higgs squared plus Higgs twins squared, all squared. So this explicitly breaks the symmetry, and you see that then it must generate a mass for the Higgs if the Higgs is the PNGB, and that mass of the Higgs will look like this, multiplied by essentially the spontaneous symmetry breaking scale. So you do actually end up with sensitivity to the spontaneous symmetry breaking scale. Let's call it F. But what is neat here is that the top partners, the fields that are sort of entering into this calculation, are not charged under QCD, which is why I said it turns out that this part is negotiable. So this is very clever. However, there's no free lunch. We can repeat this. I'm going to try and do it here. We can repeat this fine-tuning calculation. And in this case, you do, I'm not going to go through it, but it's in the notes. You do the full CCWZ construction following this thing, but now we have an SO8 fundamental and so on. You look at the spontaneously broken generators and so on. And what you get is exactly the same sort of structure. Oh my goodness, this should have been sine to the 4. Sorry about that. You get exactly this sort of structure where you end up with sine squared Higgs over F minus cosine squared Higgs over F. And then here you get sine to the 4 Higgs over F plus cosine to the 4 Higgs over F. After the lecture, I'd happily derive this for you if you're interested. And then you can repeat the calculation. And so what you can do, it's very revealing, is that you can repeat this calculation. So what I would do is you can write it like this. And what I'm going to do is put in, instead of sine squared, I'll put in this thing here. And I'll put in beta there. And I'll put this thing here instead of sine to the 4. And I'll put in beta there. So then we can compare the two. If beta goes to 0, we just recover the old PNGB Higgs story. If beta goes to 1, we recover the twin Higgs. When you do that, you can just repeat the calculation. If you've done this for your homework, you'll be able to do it yourself. And what we get is everything is the same, except that in here, there's a 1 over 1 plus beta. So in the twin Higgs story, so not only have your top partners become uncolored, essentially, or the fermions that arise to essentially fill out the multiplet under SO8, they're uncolored. But also, you win in terms of the fine-tuning you need to do to predict the observed Higgs vacuum expectation value. You win by a factor 2 as well, which is modest, but it's not nothing. And so in here, your fine-tuning goes like this, relative to the modifications of the Higgs couplings. You get 1 plus beta, so for the twin Higgs, you get beta is 1. Okay, so it's an improvement over the sort of vanilla PNGB Higgs model, but it's not an enormous improvement. But what's, I think, very compelling about these models is that they have very, and I think one of the most interesting things in general about these models is that they have totally different collider phenomenology than standard PNGB Higgs models. If I had a standard PNGB Higgs model, I would say the most important thing to do is look for this, because it's charged under QCD. It's easy, right? It's cannon fodder for the LHC. But for the twin Higgs, that thing is charged under a QCD, but not RQCD. So we can't make it at the twin LHC. We could make it in abundance, but in our LHC we cannot. So we have to look for these things in different ways. Turns out one of the best ways to look for these theories is to produce a Higgs. The Higgs will mix with the twin Higgs through interactions like this. So let's call this Higgs twin, which is like the radial mode if you work in unitary gauge, for instance. sorry, it's not, no, not through interactions like this. From the SO8 symmetric interactions, so you have things like, there's an SO8 symmetric one that looks like this, so it doesn't generate a mass for the PNGBs because it's SO8 symmetric, but you see it leads to a cross term between the two Higgs sectors. So there's some mixing. There's some mixing angle, which is proportional to sine of V over F. So that twin Higgs can then decay, just like the Higgs decays, through a twin top loop into twin gluons, which can hadronize and all sorts of things. And ultimately, they can produce states like twin mesons and so on that through the same mixing can decay back through a very off-shell Higgs into standard model particles. So one really interesting prediction of models like this is that you get showers of high multiplicity, low energy, standard model particles that might even be displaced in your detector. So dark showers, these sorts of things. I apologize for my accent. Shower is not an easy word. Shower. Okay, and so number one very valuable aspect of these twin Higgs models is that it shows where the loopholes might be, where some loopholes might be in our sort of basic preconceptions about a PNGB Higgs. And in my view, it sort of reveals to some extent how our view of naturalness through the lens of what we haven't seen at the LHC is very specific. Okay, someone yesterday at the question time said, or after questions, when we were discussing at the board, said that working on the hierarchy problem isn't very fashionable, right? And I think that is motivated, that comment, which is a very valid comment, is motivated by the fact that people expected to see, this explosion of heavy QCD charged objects, expected to see the MSSM in supersymmetry, essentially, and we didn't see it. So then the scientific thing is to say, well, what were our priors? How general were our priors? If there's a solution to the hierarchy problem, should we always expect to see colored objects produced in abundance at the LHC? If you only stare at the MSSM for 30 years, you would say yes. But then you realize that you step back and look at where the loopholes might be, and you see that actually that was a very reasonable expectation, but it was a very specific expectation based on very specific theory priors. And here's a model where the Higgs UV completion of the standard model, where the Higgs, in principle, the Higgs mass and VEV are calculable from within the UV theory. But actually, there are no new colored objects, at least until this whole thing is UV completed. Maybe they'll show some heavy colored objects will show up there, but that could be at like 5 TeV or something like this. And so revisiting theory priors and really asking honestly, how blinkered were we in our view about what we expect to see at the LHC vis-a-vis the question of Higgs naturalness, you discover a super cool and interesting set of collider predictions and things to search for. Okay, I'll finish there. We will talk for like 10 minutes, wrapping up the PNGB Higgs story tomorrow, and then we will go to cosmology and those other two options I gave where you have some sort of feedback with using, in this case, it'll be cosmology to explain a small Higgs VEV and mass and even more crazy and exotic things. So I'll stop there. Happy to take any questions now or afterwards.
What are the acceptable values for delta?
Pardon?
What are the
acceptable values? Okay, so if you do the homework question, the question is what are the acceptable values for delta? If you do the homework problem, your question will become even more pertinent. It's a qualitative thing, right? So why do we want to care about fine tuning in this sort of quasi-quantitative way? It's because we're trying to guess at what UV completes the standard model, and one way of guiding our guess is to ask how sort of baroque, particular, specific, fine-tuned does our UV completion have to be in order to predict what we observe at the LHC. And so one prior on that, one thing that might influence your prior on that is, yeah, how much fine-tuning do I have to do? And so we're using this as a guiding principle, but it's like, it's a guide, it's not a strict quantitative thing. So at what point would I personally say that I'll throw a theory, throw it out in the sense that I'm not myself going to work on it? If delta starts to approach like the few percent level, for me, I think then probably, why would nature do that? I'm not so sure. But it's a very subjective and quantitative thing. We're using it as a guide. It's like a torch, but the torch doesn't always shine everywhere. And so, it just shines in the direction you're looking. And so I wouldn't place any emphasis on strict quantitative values. If one theory is fine-tuned at 5% and the other one is fine-tuned at 10, maybe both are sort of equally plausible from that respect. Nonetheless, I would start to get uncomfortable. If it starts to get very fine-tuned, I would then ask, why would nature have done that?